Okay, go ahead. Hi, everyone. This talk is about leveraging reinforcement learning for testing distributed systems, and it's joint work with Constantin, Rupak, and Srinidhi. So distributed systems are widely used for deploying large-scale services and applications, and they usually rely on consensus protocols to work. The way these systems work is by exchanging messages with each other, and because the underlying network can fail and delay these messages, the result is a combinatorial explosion of possible reorderings and possible executions of the system. So because of this reason, even if they're widely used, their verification and testing remains very challenging. So a popular practical approach to test such system is randomized testing. What you actually do is you iteratively run the application and you explicitly simulate the network by randomly choosing the next action, for example, the next message to deliver. And you keep doing this, trying to maximize the coverage of your system states. However, since the execution space is so large, even if you run this for very long, you might still miss many possible states of the system. So our approach leverages reinforcement learning to improve randomized testing. So reinforcement learning is a machine learning paradigm where an agent iteratively interacts with an environment by observing its state and taking actions with the goal of optimizing its policy given a reward function. So in 2020, Mukherjee et al. Designed a way to map testing into an RL problem. So the execution of the system becomes the environment, and the state observed by the agent is the actual state of the system, including the state of the nodes plus the state of the network. And now the agent is the testing algorithm which will take actions to the network actions. Now to apply this, there are a few challenges, namely the choice of a reward function for such setting, and the choice of state and actions abstractions, which determine the resulting space size. So the main contributions of our work are the following. We designed a novel reward scheme for RL-based randomized testing. We discussed the role of abstractions. Then we designed an RL-based algorithm to bias testing towards interesting scenarios. And finally, we evaluate our approach, testing real-world consensus protocols implementations. So how do you choose a reward function for testing? I mean, the goal is finding bugs, but you cannot just reward when you find a bug because this is too sparse, and actually, I mean, it happens after you reached your goal. So a good proxy is to incentivize the exploration of new states. And in 2020, Mukherjee et al. Came up with a Q-learning-based algorithm where the reward was given by the negative number of visits for each state. So basically, the more one state was visited by the algorithm, the more negative its value became, incentivizing the algorithm to explore new states. So our approach is conceptually similar. We still have a bonus based on the exploration bonus based on the number of visits, which decays from 1 to 0, and we take the maximum between the immediate reward and the future discounted reward. So intuitively, what this does is to prioritize the maximum novelty along a state sequence. So in the standard Q-learning update rule, you sum them. This means that the algorithm will consider how many times each state has been visited along the path. But with our rule, it ignores how many visits you have along the path as long as it gets to new states, which is the goal in testing. Additionally, it constrains the exploration bonus within 1 and 0, which is important for our bias testing algorithm to ensure exploration there. So let me quickly introduce Raft to use as an example for the rest of the talk. So Raft is a consensus protocol where each node keeps a replica of the log. There is a leader which manages incoming requests, and these requests are appended and committed to the logs of the nodes whenever there is a quorum of nodes accepting them. Then there is a system of term numbers that the nodes can increase upon faults to start new elections if a leader fails. So when testing such systems, there is a fundamental trade-off with the choice of states and action abstractions between testing granularity and the size of the state space. So if we consider network actions, on one hand, one can choose to work with single messages. So each action is delivering specific messages, which will give us a fine-grained interleaving and potentially produce every reordering. But on the other hand, most of these reorderings will not lead to any interesting scenario for the protocol. While if, for example, we just use network partition configurations, we lose the granularity of all the possible reorderings, but in a few steps we can get to interesting scenarios like committing requests or new leader elections. Similarly, for the system states abstraction. So what kind of information do we include in the system state that we expose to the RL agent? So the information we include there will make the algorithm to explicitly explore the different values for such states of the system. But on the other hand, you definitely want to remove redundant information because this will lead to an even larger state space, and you don't want your algorithm to explore, for example, reorderings of the IDs of the node, which are not meaningful. So the type of state coverage you get strictly depends on the choice of this abstraction. So if we think about Raft and you exclude the log information, then your algorithm will definitely explore more quickly different terms and leader elected, but you lose the granularity of exploring different configurations for the logs in such states. So to tackle both the general problem of the space size and the choice of the abstraction, we designed a way to bias testing towards interesting scenarios. So the tester can define subsets of states through predicates and can build an increasingly specific sequence of such predicates to guide the algorithm towards interesting parts of the state space. So our algorithm takes this input of predicates, its sequence of predicates as input, with the last one defining the target subspace to explore. And then on top of the standard exploration bonus to increase the coverage, it provides positive rewards whenever the execution gets to these defined subsets of the state space. So in this way, the tester can define, can target specific subsets of the state space where he might have insight about being more critical or where it's more likely to find bugs. And at the same time, this helps to keep the abstraction, more information in the abstraction, because in this way, if we think about the previous example, you can keep the log information, but still you can push the algorithm to explore different leader elections, and then within that subspace, the algorithm will explicitly explore different logs configurations, so you have better granularity of your in the exploration of your target subspace. So these predicates have to be manually designed by the tester. So what we did in our evaluation, we just took generic predicates for Raft. So for example, entries added to the logs, or nodes reaching higher terms, or leader elected in higher terms, or more specific ones. For example, having two logs with the difference in their lengths, meaning that the protocol should handle the synchronization of this outdated log, which might, for example, be more likely to lead to bugs. So just to give an example, one predicate might be having an entry committed in term 2, at least one entry committed in term 2, and one possible waypoint to help the algorithm to reach there is having one leader elected in term 2, because this is mandatory to commit a request in that term. So in terms of additional required instrumentation, on top of what you need for randomized testing, which is capturing the messages and controlling the network, you just need to expose the required state information during the execution such that you can provide it to the agent. And then you need to write the code to map the system execution into an RL environment, meaning that the state information from the system should be wrapped into an environment state. And then you need to ensure that whenever the agent takes an action, this should be applied in the system execution. So to evaluate our approach, we tested 3 real-world protocol implementations, 2 based on Raft and 1 on Paxos. And in our experiments, the actions are partition configurations for the network, plus external requests to be committed, plus crashing single nodes. And the state abstraction is given by the state of the nodes plus the current partition configuration of the network. And for the node states, we consider the protocol relevant information like term numbers, the role of the node, the log information, and so on. And for the result, we ran different testing iterations, and we average the results. So the first question is, do we get better coverage with our unbiased RL-based exploration algorithm? And the answer, so these plots show the state coverage over testing time. And we compare with the previous approach from 2020 and with the random baseline. So in the benchmarks, we outperform random. So our approach is the red one. In the benchmarks, we outperform random, and we are comparable with the previous approach. In some benchmarks, we are better, but this is kind of benchmark dependent. So the second question is, can we actually bias testing towards specific states and subspaces of executions? So for doing this, we provide waypoint RL with the corresponding predicate sequence, and we measure the coverage of states of that target subspace. And here we compare with the 3 unbiased baselines that I showed before. And for this, we get significantly better coverage for most of the predicates, actually 20 out of 26 across all 3 benchmarks, meaning that we can actually bias the testing executions toward specific subspaces. And the third question is, does biasing lead to better bug finding? So during our experiments, we measured the average frequency of bugs occurrences. And this table shows it for one of the benchmarks. And as you can see, so each row is a different bug or crash. And for most of them, there is at least one bias testing scenario that achieves higher frequency, meaning that it would be easier to discover them and reproduce them by biasing testing toward those scenarios. And thank you.
So you had this thing in the beginning that the previous work had in the reward function minus something, and you change it to 1 divided by something, blah blah blah. Do you but then you have a whole bunch of other things you talk about. Do you have a way of dividing up the success into what success came from changing the reward function and what part of the success came from all the other stuff you did?
So the success of changing the reward function in the unbiased setting, so just for increasing coverage, is partial in the sense that we don't have a significantly better coverage for the unbiased setting. But so one thing is we still believe this max operator is conceptually good for testing in the sense that you really want to get to the new states. You don't want to balance exploration of the states you know. Another point is that our approach, we need our approach to build the bias testing on top of it, because when you have a negative value, you cannot balance at all between the exploration and the exploitation of these waypoints. But by providing a positive value, you can choose the reward you give in the bias testing as a hyperparameter, and you can somehow balance between how quickly the algorithm will converge to one of these executions whenever it finds a waypoint. So this is also required for the second part of the approach.
You had these very large error bars, so like in this graph you show at the end, the yellow part there is like really wide. Why is it so wide compared to the other ones?
Because I think out of at least 10 different iterations, I think for a few of them, probably the algorithm completely failed to get there, so the coverage. So when you compute the standard deviations, I mean, there's a chance that it fails to actually converge to that type of subspace. So yeah, you can have a high variety of the results. But, yeah.
Are you coming from the distributed systems applying this? This project, how did you basically end up doing this? Were you coming from distributed systems?
I think more from reinforcement learning.
So you just didn't apply it to, is there than other places where you think? Oh, you came from reinforcement learning and applied it to this distributed systems problem. Mm-hmm. Is there a similar thing you think that you can see in PL or otherwise? Or is it just
not sure.
People do consensus and other stuff. Oh, it's okay. I was just asking if you have other areas where you think it may apply, but it's okay.
I mean, it depends. You mean leveraging reinforcement learning to guide the search?
Publishing the reward to actually guide your search for the distributed system. Is it a generic thing you can keep applying to other things, or was there something special about distributed systems?
No, I mean, I think the distributed system setting is because you really have this very large space, and you can really use this idea of providing insight on where you want to explore, right? So, but yeah, the approach is somehow generalizable, but somehow you need you need a place where you can actually use it, right? So I think distributed systems are a good candidate because you really have this problem that state space is too large, so you might need to do something like this.
Okay, well, thank you.